There is no boundary, not in the way you were taught a neat line where the solar system ends and interstellar space begins, a dark shore where the sun's influence gives way to the quiet between the stars. The reality is stranger, more turbulent, and it has been pressing on us for millions of years without our knowing. In the dark of your room, while you lie still, something passes through you, not metaphorically. Trillions of subatomic particles, protons, atomic nuclei, the stripped cores of atoms accelerated by ancient supernovae pass through your body every second. They leave no mark you can feel. They come from outside the solar system, from the space between the stars. The only thing standing between you and a far heavier rain of these particles is a bubble, a magnetic membrane blown by the sun that stretches far past the planets. It is called the heliosphere, and we have recently learned that it is fragile. 2.5 million years ago, a nearby supernova compressed that bubble to within the orbit of the Earth. The cosmic radiation that followed may have helped drive extinctions in the sea. That is not speculation. The evidence is sitting in ocean sediment, and some of it is still falling now. And right now, 2 elderly spacecraft are whispering back to us that the bubble is not the safe, stable shield we assumed. Hello, and welcome to Sidereal. Tonight, the edge of the solar system, what we thought it was, what Voyager 1 and Voyager 2 actually found when they crossed it, and why the data they are still sending back are genuinely unsettling. If you would like to support the channel, please subscribe and like this video. And if you are listening from somewhere tonight, leave a comment with your location and the time. It is a small way of mapping the quiet audience across the planet. There is one more thing I would ask. If there is a question about the universe that has stayed with you, something you have wondered about in the dark and never quite resolved, leave it in the comments as well. We read them. Some of them will become the subject of future nights here. There are a few specific things I want to answer tonight. Why did the spacecraft that crossed the boundary find a magnetic field pointing the wrong way, a direction that should have been impossible? Why did the scientists wait more than a year before they were willing to say out loud that we had left the sun's bubble at all? And why does iron from an exploded star, forged before there were oceans on Earth, keep turning up in the floor of the Pacific and in Antarctic snow that fell within living memory? By the end, you will understand the strange, turbulent reality at the boundary and why the next few years may be the last time we receive data from there for a very long time. We begin with the messengers. 2 spacecraft, built in the 1970s, designed for a 4-year tour of the outer planets, now still transmitting after more than 47 years in the void. Voyager 1 and Voyager 2. They are the most distant human-made objects in existence. Voyager 1 is now roughly 25 billion kilometers from Earth, a little over 165 astronomical units. An astronomical unit is the average distance from the Earth to the Sun, 150 million kilometers. So, Voyager 1 is more than 165 times farther from us than we are from the Sunday. A radio signal, traveling at the speed of light, takes over 23 hours to cross that gap. When an engineer sends a command to the spacecraft today, the answer, if there is one, arrives nearly 2 days later. The spacecraft itself is moving at about 17 kilometers per second relative to the Sunday. At that speed, you could cross the Atlantic in under 7 minutes. And yet, out there, it will be some 70,000 years before Voyager 1 drifts anywhere near another star. And even then, not close, merely nearer than it is to anything now. It is a slow, cold coasting through an almost perfect emptiness. Try for a moment to stand where it is. You are more than 160 times farther from the Sun than the Earth is. The Sun, from here, is no longer a disk. It is a single brilliant point among the other stars, brighter than the rest, but giving no warmth you could feel, casting no light you could read by. There are no planets near you. There has been nothing near you for decades, and will be nothing near you for tens of thousands of years. Behind you, unimaginably far, is a pale blue point you could cover with the tip of a finger, and everyone who has ever lived is on it. If you called out, if the spacecraft sent a signal home at this very instant, the answer, traveling at the fastest speed the universe permits, would not reach you for nearly 2 days. That is not a delay. That is the size of the silence you are sitting in, and the spacecraft sits in it without complaint, turning its small dish back toward that blue point, and speaks, and waits, and speaks again. The two probes did not leave in the order their names suggest. Voyager 2 launched first. On the 20th of August, 1977, from Cape Canaveral, Voyager 1 followed 16 days later on the 5th of September, riding a faster trajectory that would let it overtake its twin and reach Jupiter and Saturn first. Both were lofted by Titangent Centaur rockets, and both were aimed at a rare alignment of the outer planets, an arrangement of Jupiter, Saturn, Uranus, and Neptune that occurs roughly once every 176 years, and which allowed a single spacecraft to be flung from one giant to the next, each planet's gravity acting as a slingshot. A young engineer named Gary Flandreau had worked out the geometry of that alignment in the mid-1960s. Without it, the mission as it happened could not have existed. The planets simply would not have been in the right places again for the better part of 2 centuries. The Voyagers were not the first to try the outer solar system. 2 smaller spacecraft, Pioneer 10 and Pioneer 11, had gone ahead of them in the early 1970s, proving that a probe could survive the crossing of the asteroid belt and the fierce radiation around Jupiter. Each carried a small engraved plaque, a diagram of a man and a woman, and a map showing the sun's position relative to a set of pulsars, a message meant for whoever might one day find it. The pioneers fell silent decades ago, drifting outward without instruments, without a voice. The Voyagers were the ones built to last, and to speak. What those planetary slingshots brought, along with the trajectory, was a decade of discovery that redrew the outer solar system in the public mind. At Jupiter, in 1979, the 2 spacecraft found a world more violent and intricate than anyone had pictured, a great red spot that resolved into a storm wider than the whole Earth, wrapped in bands of cloud moving past each other at different speeds, and circling it, a moon that no one expected to be alive. A young member of the navigation team named Linda Morabito, examining an image of the moon Io to fix the spacecraft's position against the stars, I noticed a faint crescent rising off the moon's edge where nothing should have been. It was a plume, a volcano, erupting, throwing sulfur hundreds of kilometers above the surface. Io turned out to be the most volcanically active body in the solar system, and no one had known until a Voyager camera caught it in the act. At Saturn, the rings dissolved under the spacecraft's gaze into thousands of individual ringlets, braided and kinked in ways that took years to begin to explain. Here the 2 paths diverged for good. The mission planners badly wanted a close look at Titan, Saturn's largest moon, wrapped in a thick orange haze that might conceal something like a young Earth. But the trajectory that would carry a spacecraft close to Titan would also fling it up and out of the flat plane in which the planets orbit, ending its tour of the planets forever. They chose to spend Voyager 1 on Titan. The gamble sent it climbing north, out of the plane, onto the long, straight road it still travels today. Voyager 2 was left to carry on alone along the plane of the planets, and in doing so it became the only spacecraft in history to reach Uranus in 1986, and Neptune in 1989, 2 ice giants that no probe has visited up close before or since. It found Uranus tipped on its side, its magnetic field wildly off-axis, and at Neptune it found winds faster than anywhere else in the solar system, and, on the frozen moon Triton, dark plumes of nitrogen venting into the thin air geysers, on a world so cold that the surface is nitrogen frost. There was one more image, and it was not scientific at all. In 1990, as Voyager 1 climbed away above the plane of the planets, the astronomer Carl Sagan persuaded the mission to turn the camera around and photograph the Earth one last time from beyond the orbit of Neptune. In the picture that came back, the Earth is less than a single pixel, a pale blue dot caught in a band of scattered sunlight, almost lost, easy to miss entirely. It was the last photograph the cameras ever took. Soon after, to save power and memory for the long dark ahead, the imaging system was switched off for good, and the software that ran it was eventually removed from the spacecraft altogether. The Voyagers went blind on purpose, trading their eyes for a few more decades of listening. They would spend the rest of their lives feeling the space around them, rather than seeing it. Consider what these machines actually are. Each carries a computer, with a total memory of a few tens of kilobytes, less than the storage in a modern car key. The instructions that run the spacecraft, that keep the antenna pointed at a planet it has not seen in decades fit in a space smaller than a single photograph on your phone. There is no modern processor aboard, no solid-state drive. The flight data system records information on a digital tape recorder, a reel of magnetic tape, a technology that was already aging when the spacecraft left the ground. When an instrument takes a measurement, it cannot send home immediately. That reading is written onto the tape first, spooled away in the cold, and then played back and radioed to Earth hours later. When a dish is listening, somewhere beyond the planets, a reel of tape from the 1970s is still winding and unwinding, holding the only record of interstellar space until the Earth can catch it. It is, in its way, the oldest working recording device off the surface of the Earth, and it is playing back messages from a place no other machine has ever been. The high-gain antenna, the dish that speaks to Earth, is 3.5 meters across. Everything else, the instruments, the fuel, the nuclear power source, is bolted to a frame that could fit inside a cube about 4 meters on a side. It weighs a little less than a small car. The signal that reaches us from Voyager 1 is almost unimaginably faint. By the time it arrives at the great dishes on Earth, the total power being collected is about 1/10 of an attawatt, 1/1000th of a billionth of a watt. To gather enough energy from that signal to light a single small bulb for 1 second, you would have to collect every photon Voyager 1 sends toward Earth across tens of thousands of years. The data rate is down to a few tens of bits per second, slower than the dial-up modems of the 1990s, slower than almost any form of communication a person under 40 has ever used. A single detailed image from the spacecraft's era, if the cameras still worked, would take many hours to send home. And yet the data trickle in. The instruments still running measure magnetic fields and plasma waves in the space around the spacecraft, and they do it powered by the steady, patient decay of a lump of plutonium. That power source is the quiet clock at the center of the whole story. Each Voyager carries 3 radioisotope thermoelectric generators devices that turn the heat of decaying plutonium into electricity, with no moving parts, nothing to wear out. The particular isotope is plutonium-238, which has a half-life of about 87 years. That is the number that governs everything, in 12. Every year, as more of the plutonium decays, the generators produce a little less heat, and so a little less power, roughly 4 watts less, each year, every year, without pause. At launch, the 3 generators together produced about 470 watts. Today, the available power is well under half of that, and still falling. The mission has become, in its final decades, a slow negotiation with physics. How to do the most science with the least electricity, as the electricity runs out. Voyager 2, on its own path past Jupiter, Saturn, Uranus and Neptune, followed a different route through the outer solar system and out the other side. It too has crossed into interstellar space. For years it carried a working plasma instrument that Voyager 1 lost early in its mission, an instrument that could measure the density and flow of the charged gas around it directly. That instrument was finally switched off in the autumn of 2024 to save power, after the geometry of its viewing angle had made its readings less and less useful. But for the years it worked beyond the boundary, it gave us something priceless. A second, independent crossing of the edge of the solar system, along a different path, more than 100 astronomical units away from the first. Together, the 2 spacecraft did not give us a single clean line marking where the solar system ends. They gave us 2 very different views of something far more complicated than a line. For most of the mission, the person holding all of this together was a physicist named Ed Stone. He became the project scientist for Voyager in 1972, 5 years before either spacecraft left the ground, and he held that role until he stepped down in 2022, half a century with a single mission. He died in the summer of 2024, having outlived, by a few years, the moment his spacecraft crossed into the space between the stars. Those who worked with him describe a particular quality, a calm that came from knowing, precisely, how much he did not yet understand. When the data grew strange, he did not rush to explain it. He waited, and when Voyager 1 finally reached the outer boundary, that patience would be tested in a way no one had planned for, because the boundary, when the spacecraft finally reached it, was nothing like the neat picture in the textbooks. The bubble we had drawn in smooth, clean lines for half a century turned out to be squeezed on one side, leaking on others, and filled with a kind of magnetic turbulence that no one had predicted. Interstellar space itself, imagined for generations as a calm and uniform emptiness, revealed itself as a restless, clumpy medium, threaded with magnetic islands and shock fronts and slow gradients of density. And the sun, carrying all of us with it, is dragging the whole arrangement through that medium toward a transition we cannot yet see. But to understand why the crossing was so strange, you have to understand the picture it overturned. And that picture, the comet-shaped bubble, the smooth shell of slowing wind, the sharp outer skin, where the sun's field meets the galaxies, was not built from measurement. No spacecraft had ever been there. It was built entirely from physics, from equations and reasonable assumptions, and it was taught as settled fact for 50 years before anything went out to check it. The idea begins with a single, radical proposal about the Sunday. In the middle of the 20th century, most astronomers believed the sun's outer atmosphere simply sat there, a hot, static corona, held in place, thinning gradually into the vacuum. The space between the planets was thought to be essentially empty, disturbed only occasionally by gusts of particles thrown out during solar storms. That was the consensus. It was wrong, and the person who overturned it was a young physicist at the University of Chicago named Eugene Parker. Parker had been thinking about the corona and about a curious observation made by others before him. Ludwig Biermann, studying the tails of comets, had noticed that a comet's tail always points away from the sun, not trailing behind the comet like smoke behind a train, but streaming directly outward, whatever direction the comet is travelling. Something, Biermann argued, must be flowing continuously outward from the sun, fast enough and steadily enough to push a comet's tail into that shape. Parker took this further. He worked through the physics of a corona heated to 1,000,000 degrees and found that it could not remain static. The pressure was too high. The hot gas had to expand, accelerating outward, faster and faster, until it was moving at hundreds of kilometers per second. He called it the solar wind, a continuous supersonic stream of charged particles pouring off the sun in every direction, all the time. The reaction was severe. When Parker submitted his paper in 1958, 2 referees recommended rejection. One senior scientist told him the idea was simply absurd, that he should go and read the literature before publishing something so obviously mistaken. The paper survived for a specific reason. The editor of the journal was Subrahmanyan Chandrasekhar, one of the great theoretical astrophysicists of the century, a man who had himself been publicly humiliated decades earlier for a correct idea about the fate of dying stars. Chandrasekhar could find no actual error in Parker's mathematics, and so, overruling both hostile referees, he published it. 4 years later, the argument ended. The Mariner 2 spacecraft, on its way to Venus, flew through interplanetary space with instruments that could detect charged particles directly. It found exactly what Parker had described, a steady wind of particles blowing out from the sun, never stopping, varying in speed but always there. Parker had been right. He lived a long life. He died in 2022, at the age of 94, long enough to see a spacecraft named in his honor, the Parker Solar Probe, fly directly through the outer corona and touch the wind at its source. There is a detail buried in Parker's story that has never been resolved, and it is worth naming, because this whole subject is full of exactly this kind of open question. Parker's wind begins with a corona heated to more than 1,000,000 degrees, but the visible surface of the sun, just below the corona, is only about 5,500 degrees. Somehow, in the thin region between the surface and the corona, the temperature does not fall as you move away from the heat source, the way heat normally behaves. It climbs by a factor of several hundred. Heat appears to flow from the cooler surface into the far hotter atmosphere above it, which ought to be impossible. How the corona is heated to the temperatures that launch the solar wind is called the coronal heating problem, and after more than 60 years of work it is still not fully solved. The wind that fills the entire solar system, that blows the bubble we live inside, begins in a piece of physics we cannot completely explain. What we do understand is the shape the wind takes as it leaves. Because the sun rotates roughly once a month, and because each parcel of wind flies straight outward while the sun turns beneath it, the magnetic field the wind carries is drawn out into an enormous spiral, the same shape water makes leaving a spinning garden sprinkler. This is now called the Parker spiral. and it wraps the entire solar system in a coiled magnetic field anchored to the turning Sunday. The wind is not uniform, either. There is a fast wind, pouring at up to 700 or 800 kilometers per second out of the open magnetic regions near the sun's poles, and a slower, denser wind of perhaps 300 to 400 kilometers per second escaping from nearer the equator. Where the fast wind overtakes the slow, it piles into rolling pressure waves that sweep outward through the whole solar system. And it is these, years later and unimaginably far out, that Voyager would feel arriving at the edge, the sun reaching across more than 100 astronomical units to tap on the boundary from the inside. The solar wind became the foundation of an entire field, and once you accept a continuous wind blowing off the sun, the shape of the whole solar system follows. The wind pours outward in every direction, carrying the sun's magnetic field with it. Because the sun rotates, that magnetic field is wound into an enormous spiral, like water from a spinning garden sprinkler. As the wind travels outward, it thins. Near the Earth, it is already sparse only a handful of particles in each cubic centimetre, moving at 300 to 800 kilometers per second. By the orbit of the outer planets, it is thinner still, but it does not blow forever. Out in the darkness, the interstellar medium, the gas and dust and magnetic field of the galaxy itself, pushes back. Somewhere, at some vast distance, the outward pressure of the solar wind falls until it can no longer hold back that external pressure. That balance point, that surface where the sun's wind finally gives way to the galaxy, is the heliopause. Everything inside it is the heliosphere. It is, in the most literal sense, the extent of the sun's kingdom. The classical picture, worked out through the 1960s and 70s, imagined this kingdom as comet-shaped. The sun moves through the surrounding interstellar cloud at roughly 25 kilometers per second, so the forward-facing side, the nose is compressed, while the trailing side stretches out into a long tail, like the coma and tail of a comet. At the nose, the boundary was thought to sit somewhere around 100 astronomical units from the Sunday. Down the tail, it might stretch for thousands, and before the wind ever reaches that outer skin, the model said, it must pass through a shock. The solar wind is supersonic. It moves faster than pressure waves can travel within it, which means it cannot gently slow down as it approaches the external medium. Instead, it slams into a standing shock wave called the termination shock, where it abruptly drops from supersonic to subsonic, heats and compresses. Beyond that shock lies a region called the heliosheath, the zone between the termination shock and the heliopause, where the slowed wind turns and drains away toward the tail. In the textbooks, the heliosheath was drawn as a smooth, orderly layer, perhaps 20 or 30 astronomical units thick, like the calm water behind a breakwater. There was one measurement, above all, that everyone agreed would settle the question of whether a spacecraft had truly left the solar system: the magnetic field. Inside the heliosphere, the field is the sun's field, wound into that outward spiral, pointing in a particular direction. Outside, in interstellar space, there is a different magnetic field entirely, the galaxy's field, draped around the heliosphere like cloth over a stone, and pointing, everyone was confident, in a noticeably different direction. So at the moment a spacecraft crossed the heliopause, its compass should swing. The magnetic field should rotate, sharply and unmistakably, as the sun's field gave way to the galaxy's. That rotation was the agreed-upon signature. It was the one prediction that could not fail. Every model agreed on it. It was the flag that would tell us, beyond any argument, that we had arrived at the edge. By the time Voyager 1 and Voyager 2 were closing in on that edge in the early 2000s, this entire picture had hardened into fact. The comet shape, the termination shock, the smooth heliosheath, the sharp heliopause, the rotating field, all of it had migrated out of the research journals and into school books. It was clean, it was reasonable, and it had never once been touched by a direct measurement. The spacecraft were about to touch it. It is worth sitting with that for a moment, because it is the quiet lesson underneath the whole night. For half a century, the edge of the solar system was drawn in textbooks with confident, clean lines. The comet shape, the smooth shell, the sharp skin, the rotating field, and generations of students learned it as settled fact. And almost none of it had been measured. It had been calculated, reasoned out from sound physics and reasonable assumptions, and then, through nothing more than repetition, it had hardened into the appearance of knowledge. There is a difference between a thing we have worked out and a thing we have checked, and it is easy to forget which is which, especially when the worked out version is elegant and has been printed in enough places. The Voyagers were about to demonstrate that difference in the most direct way possible, by going to the place the diagrams described and finding that the diagrams were wrong. Not wrong in every detail, but wrong in enough of them, and wrong in ways no one had thought to doubt. The first surprise came before either spacecraft reached the termination shock at all. The trouble was that the boundary would not hold still. The solar wind's pressure rises and falls with the sun's 11-year cycle of activity, and so the termination shock breathes in and out, moving inward when the sun is quiet and outward when it is active, by many astronomical units. Nobody knew exactly where it was at any given moment. The teams kept revising their estimates, watching for the signature of a crossing, unsure whether it would come next year or in 5 years. It was, in effect, a moving target in the dark, and the spacecraft were closing on it at 17 kilometers per second, with instruments designed decades earlier. Voyager 1 crossed the termination shock in December of 2004 at 94 astronomical units from the Sunday. It was farther out than many had guessed, though still within the range the models allowed. The crossing had, in a sense, been rehearsed. In the couple of years before the real event, Voyager 1's particle detectors had recorded strange surges that looked as though the shock might be near, and then the surges faded, and the ordinary solar wind returned. The most likely explanation is that the shock, breathing in and out with the sun's activity, had swelled outward past the spacecraft and then drawn back inside it, so that Voyager 1 was briefly beyond the boundary, then within it again, before the shock finally moved out past it for good in that December. The edge of the solar system did not simply sit and wait to be crossed. It came out to meet the spacecraft, touched it, retreated, and only later settled behind it. Even the moment of crossing, the single cleanest event the mission had, turned out on closer inspection to be a boundary that could not hold still. The crossing itself took only hours. The solar wind, which had been supersonic for the spacecraft's entire journey, abruptly slowed, dropping below the speed of sound. The temperature jumped. The magnetic field strengthened and grew turbulent. Voyager 1 had passed through the shock and entered the heliosheath, the region that the textbooks promised would be smooth. It was not smooth. Almost from the first day, the readings refused to behave. There was a particular disappointment buried in that crossing, one that mattered to the physicists more than the public ever knew. For years, theorists had expected the termination shock to be the place where a certain kind of cosmic ray was born. There is a population of particles, called anomalous cosmic rays, that had long been thought to gain their energy right at the shock, accelerated as they bounced across it. When Voyager 1 finally arrived, it expected to find the source, the engine, running, right there at the boundary. It did not. The particles were there, but their source was not where it was supposed to be. The acceleration was happening somewhere else, deeper in or farther out. By some mechanism the models had placed in the wrong location. The very first thing the spacecraft did at the edge of the solar system was to tell us that a piece of settled physics was in the wrong place. It is worth understanding what those anomalous cosmic rays actually are, because they are a clue to how the whole boundary works. They begin their lives as ordinary neutral atoms from interstellar space atoms that drift in through the heliopause because, having no electric charge, they ignore the magnetic fields that would otherwise turn them away. Once inside, sunlight and collisions strip away their electrons, turning them into charged particles that the solar wind can grab. They are then carried back out toward the boundary, and, somewhere out there, accelerated to high energy. The termination shock was the obvious candidate for the accelerator. When Voyager 1 found the shock but not the expected engine running at full strength right there, it meant the acceleration had to be happening in a more distributed, more complicated way than a single clean shock front spread along the flanks of the heliosphere perhaps, or built up gradually through the turbulence beyond. The particles were real. The tidy story of where they came from was not. There is a rhythm underlying all of this that the spacecraft made visible over decades. The sun does not shine at a constant strength. Every 11 years or so it passes through a cycle of activity from a quiet minimum, its face nearly blank, to a stormy maximum crowded with sunspots and flares, and back again. As the activity rises and falls, so does the pressure of the solar wind, and so the whole heliosphere breathes, its outer boundary swelling outward when the sun is active, and drawing inward when it is calm by many astronomical units over the course of each cycle. This is part of why the termination shock was so maddening to find in advance. It was not sitting at a fixed distance waiting to be crossed. It was moving in and out on an 11-year breath, and the spacecraft had to catch it wherever it happened to be on the day they arrived. We are not blind to this breathing here on Earth either, and that is a thread worth holding onto for later. The strength of the sun's shielding leaves a record in the ground. When galactic cosmic rays strike the upper atmosphere, they produce small amounts of particular atoms, carbon-14, beryllium-10, that then rain down and become locked into tree rings and layered ice. When the sun is active and its shield is strong, fewer cosmic rays get through, and less of these atoms is made. When the sun is quiet, more. So the rings of ancient trees and the layers of polar ice hold, in effect, a diary of how well the shield has worked across thousands of years. A record of the same modulation the Voyagers measured directly at the edge, written slowly into the chemistry of the Earth. That diary will matter when we come to the question of what a truly close explosion would leave behind. That the diary can capture sudden events, and not just the slow rhythm of the sun, was shown in a striking way not long ago. Studying the growth rings of ancient trees, researchers found that in the years 774 and 775, the amount of radioactive carbon in the atmosphere jumped sharply in a single season, a spike far larger and far faster than the ordinary solar cycle could produce. Something had flooded the upper atmosphere with radiation in a very short time. The leading explanation is an extreme burst from the sun itself, a solar storm many times more powerful than anything recorded in the modern era. But the point that matters here is the record. A pulse of radiation lasting perhaps a single year, more than 12 centuries ago, is still legible today in the rings of trees, sharp and datable to the season. If a nearby supernova or a distant gamma-ray burst ever bathed the Earth in radiation, it would not pass without trace. It would be written into the trees and the ice and the sediment, exactly as these fainter events have been. Some of the marks we have already found may be the writing of catastrophes we have not yet learned to read. Voyager 2 reached the termination shock nearly 3 years later, in the southern hemisphere of the heliosphere, in August of 2007. And here the second surprise arrived. Voyager 2 crossed the shock at 84 astronomical units, a full 10 astronomical units closer to the Sun than Voyager 1 had. 10 astronomical units is not a rounding error. This. It is more than the distance from the Sun to Saturn. The termination shock was not a sphere. It was lopsided and pushed closer to the Sun on one side than the other. Something was pressing on the bubble unevenly, squashing the southern hemisphere inward. The only thing that could do that was the interstellar magnetic field outside, bearing down harder on one side of the heliosphere than the other, denting it like a thumb pressed into the side of a balloon. Already, before either spacecraft had reached the true outer boundary, the neat comet shape was in trouble. The bubble was dented and asymmetric, shaped by an external magnetic field whose strength and direction we could only guess at. And the two crossings gave scientists something they had never had before, a way to measure the shape of the boundary by triangulation, using two spacecraft at two different latitudes, arriving at two different distances. The heliosphere was not the object in the diagrams. It was being actively deformed by its surroundings, and the surroundings were stronger than anyone had assumed. There was also a long-running argument about what lay ahead of the whole moving structure in the direction of the sun's travel. For decades, the models had drawn a bow shock out in front of the heliosphere, a standing shock wave in the interstellar medium itself, like the wave that stands in front of the bow of a boat, formed as the sun ploughs forward through the galaxy. But to make a bow shock, you must be moving faster relative to the surrounding medium than the waves that travel through it. Later measurements of how fast the sun is actually moving through the local gas and how strong the local magnetic field is suggested the sun may not be moving quite fast enough. Instead of a sharp bow shock, there may be only a gentler bow wave, a pile-up, not a crack. It is a small thing, a technical distinction. But it is another line in the textbook that turned out to be drawn with more confidence than the evidence deserved. For 8 years after that first crossing, Voyager 1 travelled through the heliosheath, and what it found there was not a calm shell of slowing wind. It was a storm. The turbulence began almost at once. Voyager 1's magnetometer, the instrument that measures the strength and direction of the magnetic field, began recording a heliosheath that bore no resemblance to the smooth, slowly turning layer the models had promised. Instead of a gentle, steady curve, the field lines twisted and folded and reversed. The field strength would spike, then collapse. Its direction could flip by 180 degrees in a matter of minutes. Plasma flows appeared from directions that were supposed to be empty. The low-energy charge particle detector, overseen by a physicist named Stamatios Krimigis of the Johns Hopkins Applied Physics Laboratory, recorded bursts of particles that made no sense for a spacecraft drifting through a placid medium. Krimigis, known to his colleagues as Tom, had been with Voyager since before it launched, and had spent decades watching the solar wind flow past the planets. He knew its rhythms the way a sailor knows the sea. What arrived from the heliosheath matched no rhythm he recognized. For the first 2 years after the crossing, the team struggled to interpret it. It looked, at first, like noise. It looked like instruments beginning to fail after 30 years in the cold. But the same patterns appeared across multiple detectors at once, correlated, real. Slowly, a picture assembled itself, and it was a picture no one had drawn before. The heliosheath was filled with enormous magnetic bubbles. Each one was a self-contained structure, roughly 100 to 200 million kilometers across, about the size of the Earth's entire orbit around the Sunday. They formed through a process called magnetic reconnection. The solar wind carries the sun's spiraling magnetic field outward, and over billions of kilometers, near the boundary, that field becomes tightly wound and folded back on itself. Where oppositely directed field lines are pressed together, they can snap and reconnect, pinching off closed loops of magnetic field sausage-shaped islands, sealed off from the field around them. And once formed, these islands drift through the heliosheath like foam riding the surface of a breaking wave. Voyager was not crossing a calm shell, it was passing through a layer of magnetic froth. To picture where that froth comes from, you have to picture the shape of the sun's magnetic field far from the Sunday. The sun is, very roughly, a bar magnet with a north and a south, and the two halves of its field are separated by a thin, warped sheet that spirals out through the entire solar system, a surface where the field points one way on the sheet's upper side and the opposite way on its lower side. Because the sun's magnetic poles are tilted relative to the axis it spins on, this dividing sheet is not flat but wavy, rippling as it sweeps outward, so that it flares and folds like the skirt of a spinning dancer. The scientists who first described it actually called it the ballerina skirt. Every time the sun turns, a spacecraft far out at the edge passes from one fold of this skirt to the next, crossing from field pointing inward to field pointing outward and back again. Near the termination shock, where the wind slows and the field bunches up, these oppositely directed layers are crushed together tightly enough that they snap and reconnect, and the froth of sealed magnetic bubbles Krimigis found is what that crushing and snapping produces. The chaos at the edge of the solar system is, in a real sense, just the sun's own tilted magnetism, wound tight over billions of kilometers and finally breaking apart against the wall of the galaxy. The physics of how such structures form near the heliosphere was worked out in detail by theorists including Merav Ofer and James Drake, whose computer models showed that the folded, sectored magnetic field near the boundary would naturally break down into exactly this kind of froth. What the models predicted, Voyager's tangled data confirmed. The discovery was published in the journal Nature in 2011, with Krimigis among the authors under a title that was almost flat in its plainness: Magnetic Bubbles at the Edge of the Solar System. The plainness of the title hid the size of the implication, because if the outer region of the heliosphere is a chaotic foam of magnetic islands rather than a smooth, sealed shell, then the boundary of the solar system is not a wall. It is a shifting, porous maze. An IT4, 1D, galactic cosmic rays trying to enter from outside would sometimes be trapped within the bubbles, bouncing from field line to field line, delayed and scattered, and sometimes, where the bubbles opened gaps, they would pour straight through. The protection the heliosphere offers is not uniform, and it is not constant. It is patchy, it changes with time, and it depends on the detailed structure of a froth that no instrument can photograph. That last point is worth sitting with. Voyager carried no camera that could see a magnetic field. The bubbles were never imaged. Their existence was inferred entirely from the fingerprints they left in the data. The sudden reversals in the magnetometer, the correlated jumps in particle counts, matched against simulations of how such structures must behave. It was like standing inside a thunderstorm on a black night and working out the shapes and sizes of the clouds from nothing but the flashes and the gusts of wind against your face. Voyager was inside the storm, blind, feeling the shape of it with instruments, and sending home a description of something it could not see. Voyager 2, entering the heliosheath in the southern hemisphere in 2007, found similar turbulence, though its path ran through a somewhat less violent region. The difference between the two confirmed that the chaos itself was uneven, some parts of the boundary layer more turbulent than others, shaped by how hard the external field pressed on each side. The single smooth curve of the textbook diagram was gone for good, replaced by a churning zone of magnetic storms each the size of an inner solar system. And there was a part of the bubble neither spacecraft would ever visit. Both Voyagers left through the front and flanks of the heliosphere in the general direction of the sun's motion. Neither went down the tail, the long region streaming out behind us, away from the direction we travel. In the old comet picture, that tail stretched for thousands of astronomical units, a fading wake behind the moving bubble. But with the froth and the asymmetry now on the table, even the tail's basic shape came into doubt. Some models, built from the way the interstellar field grips the bubble, suggested the tail might not be a single long streamer at all, but might split into two great lobes, like the two trailing tails of certain comets, or fold the whole heliosphere into a shape more compact and more curled than anyone had drawn. We have no spacecraft down the tail, and no realistic prospect of sending one. Its shape is inferred from physics and from faint maps of atoms, and it remains, to this day, one of the genuinely unsettled features of the place we live. Voyager 1 spent 8 years crossing this region, a layer the models had predicted might be 20 or 30 astronomical units thick, and which turned out to fall roughly within that range, but to be infinitely more complicated inside than anyone had drawn. Voyager 2, crossing later along its own path, measured a heliosheath of a somewhat different thickness on its side of the bubble, confirming once more that the shell is lopsided thicker where the interstellar medium presses less hard, thinner where it presses more. Even the width of the boundary layer depends on which direction you leave through. 8 years is a long time to travel through anything, even at 17 kilometers per second. Down on Earth, presidents changed, children were born and started school, and the data trickled in the whole while at a few tens of bits per second, one fluctuation at a time. The scientists watched, and waited, and argued about what it meant, and the entire time a single question hung over the mission, sharp and specific. The magnetic field inside the heliosheath still matched the sun's spiral. The interstellar field outside, everyone was certain, pointed in a completely different direction, perhaps 60 or 90 degrees away. So when Voyager finally crossed the heliopause, the compass would swing. That rotation would be the flag. It was the one thing everyone agreed on, and when the moment came, the compass did not move. Voyager 1 crossed the heliopause on the 25th of August, 2012, at a distance of 121.6 astronomical units from Earth. It did not happen as a single sharp event. It came as a cascade of changes that unfolded over hours. The low-energy charged particle instrument recorded a sudden, dramatic collapse in the count of hot, low-energy ions, the particles that come from the sunday. At the same moment, the cosmic ray detector recorded a sharp jump in galactic cosmic rays, the high-energy particles accelerated by distant supernovae and pulsars, the radiation of the wider galaxy. The two curves crossed like the blades of a pair of scissors. The sun's particles fell away. The galaxy's particles flooded in. For the teams who ran those instruments, the reading was unambiguous. Voyager 1 had left the solar bubble. It was in interstellar space. The change was startlingly sharp. Over a matter of days, the count of the sun's own particles dropped by a factor of hundreds nearly to nothing, while the galactic cosmic rays rose to a steady new level and stayed there. For anyone watching those two instruments alone, there was no ambiguity at all. This was the moment the mission had been built for, across 40 years and 12 billion kilometers. Some of the scientists wanted to announce it at once, and this is where the discipline of the mission showed. Science has a long memory for premature announcements, for the boundary claimed too early, the discovery retracted, the excitement that outran the evidence. To stand at the edge of the solar system, to have half your instruments screaming that you have crossed it, and to say instead, "We are not yet sure," requires a particular kind of restraint. Ed Stone had it. He would not announce a crossing that his own magnetometer team could not, in good conscience, confirm. But the magnetometer told a different story, and the magnetometer would not be argued with. The field strength rose, as expected. The field direction did not change. It held, within a few degrees, to the same spiral orientation it had carried for years inside the heliosheath. The compass, which was supposed to swing through 60 or 90 degrees, barely twitched. The magnetometer team was led by Leonard Berliger at the Goddard Space Flight Center. Their data were clean, precise, and impossible to dismiss. The interstellar magnetic field was supposed to have its own independent direction, set by the motion of the local cloud and the deep history of the galaxy in this part of space. For it to be aligned so closely with the Sun's field was, under the standard picture, essentially impossible, and so Berliger's team could not, in good conscience, confirm the crossing. Their single most important measurement said the spacecraft had not left. Now the mission had a genuine crisis, and it was a crisis of the best kind. Two sets of instruments, both working perfectly, both trusted, telling two irreconcilable stories. The particle physicist said Voyager was outside. The magnetometer physicist said it could not be. Ed Stone sat between them, holding a question that no single instrument could answer, and he refused to announce a crossing that half his own team could not endorse. And so the mission entered a holding pattern that would last more than a year, a strange, quiet interval in which the most distant human object in the universe had, by one reading, just made history, and by another reading had not moved at all. Through those months, Voyager 1 kept coasting outward past 122 astronomical units, then 123. The particle instruments went on describing an interstellar environment. The magnetometer went on describing a field that should not exist outside the heliosphere. In the meetings, the disagreement was professional and real. Cremigis argued that the models of the interstellar field were simply wrong, that the galaxy's field near the boundary had been combed into alignment with the sun's by forces the models had left out. That idea was not a comfortable one, because it undid a convenient assumption. Scientists had treated the galaxy's magnetic field near the sun as something fixed and external, a fact you could look up, pointing in a direction set by the wider structure of this arm of the Milky Way. But if the heliosphere itself reaches out and bends that field, draping and stretching it around the bubble for a great distance before it settles back to its natural direction, then a spacecraft crossing the boundary would not find the galaxy's true field at all. It would find the galaxy's field distorted by our own bubble, pulled into local alignment with the sun's, which is exactly what the compass showed. The measurement that had been chosen precisely because it was supposed to be clean, external, and independent of any model turned out to be reporting on a region the sun still quietly controls. When Voyager 2 crossed the heliopause 6 years later, along a completely different path, its magnetometer found the same thing, the field holding its direction across the boundary rather than swinging. Two spacecraft, two crossings, the same impossible result. It was not a fluke of one instrument or one location. It was how the boundary actually behaves. Berliger's team replied that a field direction is a direct measurement, not a theory, and that it demanded to be explained rather than explained away. Stone listened and asked questions and did not rush. It is worth remembering that he had already waited 40 years for this. He could wait a little longer, to be sure. The instrument that finally broke the deadlock was one that did not measure the magnetic field at all. It measured sound, or something very like sound. The plasma wave subsystem, built and run for decades by Don Gurnett at the University of Iowa, listened to oscillations in the plasma itself, the trembling of the charged gas around the spacecraft. And it was about to hear something no human instrument had ever heard. To understand what Gurnett's instrument heard, you have to understand a small, elegant piece of physics. A plasma, a gas of charged particles, electrons and ions, is not silent. Disturb it, and the electrons are pushed out of place and then pulled back by the electric attraction of the ions they left behind. They overshoot and swing back and overshoot again, oscillating at a natural frequency. And here is the useful part. That frequency depends on only one thing: how many electrons there are in a given volume. Denser plasma rings at a higher pitch. Thinner plasma rings lower. Measure the pitch, and you have measured the density directly, with nothing else required. It is one of the cleanest measurements in all of space physics. Gurnet's instrument sensed these oscillations through a pair of long antennas, 10 meters each, that picked up the faint voltage the trembling electrons induced. From the frequency, he could read off the number of electrons per cubic centimeter in the space around the spacecraft. Inside the outer heliosheath, that number was low, roughly 0.002 of an electron per cubic centimeter. In true interstellar space, the models predicted a jump to something like 0.05, or even a tenth. So a single plasma wave measurement could settle the entire argument with one number: inside or outside. The pitch would tell. But there was a problem, and it was the same problem that governs everything on Voyager: power. The plasma wave instrument drew electricity, and Voyager's supply was already dwindling. Gurnet could only switch it on for short campaigns, a few times a year, carefully scheduled so as not to drain the razor-thin margin the spacecraft lived on. For decades he had nursed the instrument along, turning it on, listening, turning it off, waiting for the moment it would be needed. In the spring of 2013 he turned it on again, and this time, in the data stream, there was something that had not been there before. The instrument recorded oscillations at a frequency of about 2,000 cycles per second, 2 kHz, a high, thin electronic tone. Gurnet had long made a practice of converting plasma wave data into audible sound, so the team could hear the shape of the space around the spacecraft. He did it now. The sound that came back from Voyager 1 in the spring of 2013 was a faint, steady whistle, and that whistle carried a number. The plasma around the spacecraft held about 0.08 of an electron per cubic centimeter, 40 times denser than the heliosheath. That density could come from only one place: the interstellar medium. The sound itself was not dramatic. It was thin and constant, like wind moving across the mouth of an empty bottle, a single held note in the dark. But no human being had ever heard it before. No instrument had ever been there to record it. It was the sound of the sun's bubble ending and something vast and cold beginning, and Gurnet converted it into an audio file and played it for his team in a conference room in Iowa. For a few seconds, the people who had spent their lives on this mission sat and listened to the actual sound of interstellar space. Don Gurnet had been building instruments like this since he was a student in the early 1960s, and he had flown them on dozens of missions across his career. He had a particular gift for turning the invisible physics of plasma into something a person could actually hear. And over the years, the recordings he made the eerie chorus of waves in the Earth's own magnetic field, the roar of the radiation around Jupiter, and now the thin whistle of interstellar space travelled far beyond the scientific journals, played in lecture halls and planetariums, the true voices of places no human being will ever stand. He kept the Voyager instrument alive through decades of dwindling power by sheer patience, switching it on for brief windows, listening, switching it off, guarding its slice of the shrinking electrical budget. He died in the early days of 2022, a few weeks before Eugene Parker. In the same year, Ed Stone stepped down the generation that had built and understood these machines beginning, quietly, to leave. There was a second kind of listening his instrument made possible. When a large shock wave from the sun finally reaches the interstellar plasma, it does not simply ring it at one clean note, it stirs it, and Gurnet detected what he called tsunami waves, great disturbances rolling out from the sun, crossing the heliopause into the space beyond, and setting the interstellar medium trembling for months at a time. He tracked several of these in the years after the crossing. Each one was a reminder that the boundary is not a sealed wall but a membrane, and that the sun can still reach through it and disturb the galaxy on the far side. Voyager 2, when it crossed the heliopause in 2018, added something its twin could not. It still carried a working plasma instrument, the one built long before by a team including John Richardson at the Massachusetts Institute of Technology that could measure the density, speed, and temperature of the charged gas directly, rather than inferring the density from a ringing note. When Voyager 2 passed into interstellar space, that instrument returned the first direct measurements of the plasma there, and they matched what Voyager 1 had been whistling home. The interstellar medium was denser than the models had promised, and it too showed the density rising with distance. The temperature it measured was strangely high, some 30 to 50,000 degrees, and yet the gas was so thin that a hand held out in it would feel no warmth at all, only the deep cold of a place with almost nothing in it to carry heat. For as long as that instrument kept working beyond the boundary, it gave us the only direct touch we have ever had of the gas between the stars. On the 12th of September, 2013, more than a year after the crossing had actually happened, Ed Stone announced it to the world. His words were plain. We are in interstellar space. Crimigis, who had pushed for the announcement earlier, later offered his own four-word summary of what the whole episode had taught them. The model is wrong. He did not mean the crossing had not happened. He meant that the entire framework for understanding the magnetic field at the boundary, the framework that had guided every prediction for 40 years, was mistaken. The galaxy's field near the heliosphere was aligned with the sun's in a way that no one could fully explain, and if that was true, then the shape of the heliosphere was not the familiar comet with its long tail. It was something else, perhaps a rounder, more compressed shape. Perhaps something stranger still later modelling by Ofer and others would even suggest a form more like a folded croissant than a comet, though that remains an open argument to this day. The compass that did not move had taken the tidiest diagram in the textbook and quietly torn it up. It is worth being precise about what Voyager had, and had not, done. When Ed Stone said the spacecraft was in interstellar space, he meant it had left the heliosphere, passed beyond the sun's wind, out of the magnetic bubble, into the medium of the galaxy. He did not mean it had left the solar system, and the difference is larger than it sounds. Far beyond the heliopause, far beyond anything Voyager has reached or will reach, the sun's gravity still holds sway over a vast cloud of comets, that faint spherical shell, reaching perhaps a quarter of the way to the nearest star. By the measure of gravity, the solar system does not end at the heliopause. It ends somewhere out in that comet cloud, and Voyager 1, for all its speed and all its decades, is only a small fraction of the way to its inner edge. The spacecraft has left the sun's atmosphere, its wind, its magnetic shelter. It has not left the sun's gravitational family, and at 17 kilometers per second it would need roughly another 30,000 years to cross the comet cloud and be truly free of the Sunday. There are, in other words, at least two edges to the solar system, and they lie enormously far apart. Voyager has crossed the near one. The far one it will pass, still bound to the sun, long after the last of its power is gone. And the plasma wave measurement did more than confirm the crossing. It revealed something no one had ordered. When Gurnet's instrument recorded the density at the heliopause, the number was 0.08 of an electron per cubic centimetre. But when the plasma rang again a couple of years later, as Voyager pushed deeper, the density had risen to nearly 0.11. By 2019, it was approaching 0.13. The interstellar medium was not only denser than expected, it was still getting denser the further out the spacecraft travelled. Voyager was climbing a slope that no map had drawn. Something lay ahead of it, larger and thicker, and the solar system was moving toward it. No one is certain what that rising slope is. It may be that the heliosphere has swept a hollow around itself, thinning the gas nearby, so that the density Voyager measures simply climbs back toward the true level of the surrounding cloud as the spacecraft moves out of the hollow. Or it may be something more consequential, the leading edge of denser material, the boundary of our little cloud approaching from ahead, the first hint of the transition the sun will eventually make into whatever lies beyond. The two spacecraft cannot yet tell these possibilities apart, because they are only 2 points, moving slowly, in a structure that spans light years. But the direction is not in doubt. Whatever the solar system is heading into, it is denser than where we have been, and we are heading into it now. That rising density became a mystery in its own right, and following it takes us into the strange, layered structure of the space just beyond our door. The whistle Gurnett played for his team in the spring of 2013 was not a single event. It came back. The plasma wave instrument recorded the same kind of tone again a year later, in 2014, and a third time in 2020, each time triggered by a shockwave from the sun that had travelled all the way out and rung the interstellar plasma like a struck bell. And each time, the pitch was a little different, and the density it revealed was a little higher than the time before. The relationship between pitch and density follows a simple law. The frequency rises as the square root of the density double the number of electrons, and the tone rises not by double, but by about half again. In the spring of 2013, the pitch told Gurnett that the plasma held roughly 0.08 of an electron per cubic centimetre. By the 2014 event, it was closer to 1/10. The 2020 event, recorded more than 20 billion kilometres from Earth, gave a value approaching 13/100. Voyager was not passing through a uniform interstellar medium. It was climbing a persistent, steady gradient, a slow thickening of the gas, year over year, with no sign of levelling off. Some increase had been predicted. There is a structure the models called the hydrogen wall, and it arises from a process that operates wherever the solar wind meets the incoming interstellar gas. It is called charge exchange. A fast-moving proton from the solar wind meets a slow, neutral hydrogen atom drifting in from outside and steals its electron. The proton becomes a neutral atom and goes streaking off in a straight line. No longer held by any magnetic field, the atom it robbed, now missing an electron, becomes an ion and is swept up by the solar wind and carried along. Repeated across the whole boundary, this swapping of identities piles up neutral hydrogen just outside the heliopause, a wall of atoms, compressed and warmed, glowing faintly in ultraviolet light. Voyager 1 actually carries an ultraviolet instrument, left over from the planetary flybys, and in the decades after Neptune it was turned to watch for the particular glow that hydrogen gives off. As the spacecraft approached the edge, that glow brightened, right where the models had placed the wall. The Hubble Space Telescope, looking toward nearby stars, saw the same signature written in the light of those stars: neutral hydrogen piled up at the edge of our heliosphere, and at the edges of other stars' heliospheres too. The wall was real. It was where it should be. That last point is quietly profound in its own way. Every star that blows a wind, which is to say, most stars, carves out its own bubble in the interstellar medium, its own private heliosphere, with its own wall of piled-up hydrogen at the edge. Astronomers can detect these bubbles around nearby stars by the same absorption signature, reading the shape of another star's shield in the light that passes through it. The heliosphere is not a peculiarity of our Sunday. It is one example of a thing that surrounds nearly every star in the galaxy. Countless bubbles, of every size, blown by every kind of star, overlapping and jostling across the whole disk of the Milky Way. We happen to live inside one of them, and we have sent 2 machines to its edge, but the galaxy is full of these fragile membranes, each one sheltering whatever lies within it from the same cold rain. But it could not explain what Voyager kept finding. Because the hydrogen wall, in the models, is a wall. The density should peak right at the heliopause, where the pressures balance, and then fall away as the spacecraft moves into the open interstellar medium beyond. Instead, the density kept climbing. By 2019, it was more than half again what it had been at the crossing, and still rising. The wall was not a wall so much as the near edge of a long, rising slope, and Voyager was still walking up it. Something beyond the wall was denser than the models had allowed. The local patch of galaxy we are entering is thicker than the patch we have been in. Before we follow the sun forward into that thicker gas, the rising density forces a question we can no longer avoid. If the shield around us is not a sealed wall but a porous, shifting boundary, then how well is it actually protecting us right now? The Voyagers could answer this, because one of the instruments that ran longest on both spacecraft was built precisely to count the thing the shield is supposed to keep out: galactic cosmic rays. These are the high-energy particles, protons, helium nuclei, the stripped nuclei of heavier atoms, accelerated to nearly the speed of light by supernovae and other violent engines scattered across the galaxy. Inside the heliosphere, their numbers rise and fall with the sun's 11-year cycle. When the sun is active, its tangled, strengthened field sweeps more of them away before they can reach the inner planets. When the sun is quiet, the shield weakens, and more get through. This link between solar activity and cosmic ray intensity was one of the first things the Voyagers confirmed on their way out. The reasonable expectation was that once a spacecraft crossed the heliopause and left the sun's field behind, this modulation would simply stop. Outside the bubble, the count should settle to a steady, raw level, the full, unshielded intensity of the galaxy, changing only over the immense timescales on which the galaxy itself changes. That is not what happened. From the moment Voyager 1 crossed into interstellar space, its cosmic ray counts kept fluctuating in ways that should not have existed outside the bubble. Some of the changes were plainly the sun's doing. When one of those great pressure waves reached the boundary and pushed across it, Voyager would record a temporary dip in galactic cosmic rays, as though the shock had briefly swept a path clear through the medium ahead of it, the sun, from more than 100 astronomical units away, still able to reach out and thin the radiation around the spacecraft for a while. These solar-driven dips confirmed, once more, that the boundary leaks in both directions. But there were other changes, with no solar trigger at all, dips and rises that came and went over weeks and months, matching nothing the sun had done. The most natural reading was that Voyager was passing through structure in the interstellar medium itself, patches where the magnetic field was stronger or weaker, denser and thinner regions, perhaps the faded remnants of shock fronts from other, older stellar explosions drifting through the local gas. The space beyond the heliosphere was not only lumpy in its density, it was lumpy in its very ability to block or emit radiation, and the spacecraft was sailing slowly through those lumps, reading them off one by one. And then, in the early months of 2020, something happened that no one had expected so far out. Voyager 1's cosmic ray detector recorded a sudden, deep, sustained drop in the flux of high-energy particles, a plunge almost as steep as if the spacecraft had somehow slipped back inside the heliosphere. For several months, the radiation environment around Voyager 1 looked like the inside of the bubble rather than the outside of it, and yet the spacecraft was well over 150 astronomical units from the Sun, tens of astronomical units beyond the heliopause, and had been in interstellar space for nearly 8 years. It was seeing something that, by the simple picture of inside and outside, had no business being there. The anomaly was studied by a team including the physicist Jamie Rankin, who had spent years working through Voyager's records. The explanation that emerged was as elegant as it was unsettling. The spacecraft, they concluded, had most likely drifted into a magnetic island, a disconnected loop of the sun's own magnetic field that had pinched off from the heliosphere and floated free into interstellar space, carrying its own trapped field. And its own shielding with it. Picture a smoke ring detached from a rising column, drifting across a dark room on its own. Inside that island, Voyager was partly shielded from the galaxy's cosmic rays once more, not by the heliosphere, but by a stray fragment of it that had broken away and gone wandering. After some months, the spacecraft passed out the far side, and the cosmic ray count climbed back up. The implication reached back and tied the whole story together. The magnetic bubbles Cremigis had found churning inside the heliosheath were not necessarily trapped within the boundary. They could break free, pinch off entirely, and drift outward into interstellar space, carrying fragments of the sun's influence with them for who knows how far. The edge of the solar system in this picture is not a surface at all. It is a frayed, fingered region, shedding pieces of itself into the galaxy, so that the line between inside and outside blurs into a zone a spacecraft can take months to cross, even when it is, by every other measure, already long gone from home. This ragged, leaking picture was confirmed from an entirely different vantage point, not from a spacecraft out at the boundary, but from one orbiting close to the Earth. In 2008, a small mission called the Interstellar Boundary Explorer was launched, with a single clever purpose: to map the whole edge of the heliosphere at once, from the inside, by collecting the neutral atoms it throws off. Here, the charge exchange process that builds the hydrogen wall becomes a tool. Out at the boundary, fast charged particles are forever stealing and swapping electrons with slow neutral atoms, and some of the newly neutralized atoms go flying inward in straight lines, unbent by any magnetic field, carrying a record of the conditions where they were made. The orbiting explorer collects these atoms, patiently, one at a time, and builds from them an image of the boundary much as a telescope builds a picture out of light, except that this instrument builds its picture out of individual atoms arriving from the edge of the solar system. When the first full map was assembled, it held something no one had predicted. The team, led by the physicist David McComas, had expected a broad, smooth glow, brightest in the direction where the heliosphere ploughs head-on into the interstellar medium. Instead, arcing across the map was a narrow, brilliant ribbon, a long, sinuous band of atoms far brighter than anything around it, stretching across a large fraction of the sky. Nothing in any model had called for it. McComas described the result as genuinely shocking, and for a time no one could say what it was. The leading explanation traces the ribbon back, once again, to the interstellar magnetic field draped around our bubble. In a narrow band where that external field wraps the heliosphere at just the right angle, where the field lines run side-on to our line-of-sight atoms that have swapped their charges become briefly trapped, circling in place, before some of them neutralize again and come streaming back inward to be caught near the Earth. The ribbon, in other words, is a kind of magnetic fingerprint, a bright line in the sky that traces the shape of the galaxy's field pressing against our shield. And it is not fixed. The orbiting mission has watched it brighten and fade and shift with the sun's cycle, a slowly moving portrait of a boundary that is always responding to the sun on one side, to the galaxy on the other. Put the two together, the Voyagers feeling the boundary from within it, and the orbiting mission imaging it from afar, and the old diagram is gone beyond recovery. The heliosphere does not protect us by being a solid wall. It protects us by being a complex, uneven, living filter, thicker in some directions and thinner in others, leaking here and sealing there, shedding pieces of itself into the dark, and changing its effectiveness from one year to the next as the sun breathes and the galaxy presses back. The radiation that reaches you tonight is not held off by a fixed barrier. It is held off, imperfectly and unevenly, by a standing negotiation between the sun and the galaxy, and the terms of that negotiation are always shifting. Which brings us back to the question the rising density first raised. The local conditions the Voyagers are measuring, the density, the field, the leaking shield, are not permanent. The sun is moving, carrying the whole heliosphere with it, through a region of the galaxy with its own geography of denser clouds and emptier cavities. If the medium outside is clumpy, and the shield is already being squeezed and dented by it, then everything depends on what lies ahead. And to know what lies ahead, you have to know where we are. The sun is not sitting in empty space. It is embedded in a specific cloud of gas, a warm, wispy structure called the local interstellar cloud, or, less formally, the local fluff. It is about 30 light-years across, warm by interstellar standards at around 7,000 degrees, and thin, almost beyond imagining, roughly 3/10 of an atom in every cubic centimetre. That is far emptier than the best vacuum ever made in a laboratory. And yet, even that whisper of gas is enough to press on the heliosphere, to dent it, to shape it. We are near the inner edge of this cloud, where the heliosphere has swept some of the material aside, which is part of why Voyager is finding the density rising as it pushes outward toward regions the sun has not cleared. We know the direction this gas comes from with real precision, because we can feel its wind. The neutral atoms of the local cloud drift through the heliopause as though it were not there unbothered by magnetic fields. They sail straight in, and spacecraft near the Earth have caught them and measured their direction and speed. There is, in effect, an interstellar wind blowing through the solar system, a thin, steady breeze of helium and hydrogen atoms streaming in from the direction of the constellations Scorpius and Ophiuchus at around 25 kilometers per second, the signature of our own motion through the cloud. It has been blowing through the solar system the whole time, through every human life that has ever been lived, through this room, through you, and no one felt it until we built instruments delicate enough to count single atoms arriving from between the stars. The cloud carries dust as well as gas, tiny grains of solid interstellar material, forged in the cooling atmospheres of dying stars and in the shockwaves of old supernovae. Spacecraft in the outer solar system have caught these grains directly, sampling the solid debris of the galaxy as it drifts past, weighing individual specks of matter that formed around other stars. And our cloud is not alone. It is one of a small cluster of similar wisps, each a few light-years across, drifting together through the emptier cavity around them. Just ahead of us, in the direction the sun is travelling, sits a neighbouring cloud, slightly different in its properties, and no one is certain exactly where our cloud ends and the next begins, whether they are gently merging or quietly colliding along a shared front. That uncertain frontier is the one the sun is approaching now. We drifted into this cloud sometime in the last 100,000 years. The exact figure is uncertain, somewhere between 40,000 and 150,000 years ago, and we are near the far side of it now. The cloud's outer edge, in the direction the sun is travelling, may be only a few thousand astronomical units ahead. That sounds enormous, and in human terms it is hundreds of billions of kilometres. But in galactic terms it is nothing, a step across a room. Voyager 1, our farthest scout, has covered less than a tenth of the way to that edge. The transition is coming, on a timescale short enough to matter to the history of life, though far too long to matter to any of us. And what lies beyond the cloud is stranger still. Our cloud, and several neighbouring clouds like it, sit together inside a vast, nearly empty cavity called the local bubble, a region roughly 300 light-years across, blown clear by a series of supernovae that began detonating 10 to 20 million years ago. Inside the bubble, the gas is hot and desperately thin, 1,000,000 degrees or more, thinner than the cloud we currently occupy by a wide margin. It is, in effect, a hole in the interstellar medium, carved by ancient violence. Our little cloud is a drifting wisp of denser fog inside that hole, and the sun is passing through the fog on its way to somewhere else. The bubble's existence was first proposed in the 1970s and 80s to explain a faint, diffuse glow of low-energy X-rays that seemed to come from every direction in the sky. That glow made sense if the solar system was surrounded by a shell of hot gas, slowly cooling and emitting X-rays as it did. A German X-ray satellite launched in the early 1990s mapped that glow across the whole sky and confirmed the picture. The local bubble is real, and it is not a neat sphere but an irregular cavern, with tunnels and openings connecting it to other, older bubbles carved by other, older supernovae. The galaxy, seen this way, is not a smooth sea of gas. It is a froth, a network of bubbles and shells and filaments, constantly being reshaped by exploding stars. And here recent work has added something remarkable. In 2022, a team led by Catherine Zucker and Alyssa Goodman mapped the young stars and star-forming clouds around us in 3 dimensions and found that nearly all of the nearby stellar nurseries sit on the surface of the local bubble, swept up and compressed on its expanding shell, like debris on the crest of a wave. The bubble did not just clear a cavity, its expansion triggered the birth of the very stars we see forming around us. And the sun, drifting through, happens right now to sit almost exactly at the centre of that cavity, not because there is anything special about our position, but because we have wandered into the middle of an old wound in the galaxy that is still, slowly, healing. Step back far enough and even the local bubble is a passing feature. The sun does not sit still in the galaxy. It orbits the centre of the Milky Way, carrying the whole solar system with it, at roughly 230 kilometers per second. And even at that speed, a single orbit takes something like 230 million years. The last time the sun was on this side of the galaxy, in this phase of its orbit, the largest animals on Earth were the early dinosaurs. In the course of that long circuit, the sun rises and falls gently through the crowded plane of the galaxy and drifts into and out of the spiral arms, where the gas is denser and the young, massive, short-lived stars, the ones that end as supernovae, are concentrated. The environment just outside the heliosphere is not a fixed address. It is a landscape the sun is travelling through, and over millions of years it changes completely. Thin hot cavities, dense cold clouds, quiet stretches, and dangerous crossings where supernovae are more common. The iron in the sea floor is a record of one such passage. There have been others we cannot read, and there will be others we will not be here to see. The heliosphere has been swelling and shrinking in response to this changing weather for 4.5 billion years, and it will go on doing so, indifferent to whether anyone is inside it keeping track. There is a thought that follows from this, and it is worth naming carefully because it is a hypothesis rather than a settled fact. Some scientists have suggested that a star's location in the galaxy matters for whether life can take hold and endure that too close to the crowded, violent centre, or too often inside the dense spiral arms where supernovae cluster. the radiation and the gravitational disturbances might come too frequently for complex life to survive the long stretches of quiet it seems to need. The Sun's orbit around the galaxy happens to be gentle and nearly circular, keeping it out of the worst of the traffic, neither plunging toward the center nor lingering long in the densest arms. Whether that steadiness has been necessary for life on Earth, no one can say for certain. It may be that life is hardier than we think, or that the dangers are more evenly spread than this picture suggests. But it is at least possible that our existence owes something not only to the Earth's distance from the Sun, but to the Sun's particular path through the galaxy, a quiet lane, on a long road, that has kept the worst of the weather at arm's length for most of the time it mattered. The Sun's motion carries us roughly toward the constellation Hercules and toward the far edge of our little cloud. When we reach that edge, one of two things will happen. If the cloud ends sharply and gives way to the hot, thin gas of the bubble, the pressure on the heliosphere will drop, and our bubble will expand, the termination shock and heliopause moving outward, the shield inflating like a balloon rising into thinner air. For a time, we would be more exposed to some things and better shielded from others, or the cloud may not end cleanly. There may be denser clumps at its edge, or another small cloud pressing against ours. If we pass into denser gas, the pressure will rise, and the heliosphere will be squeezed, the boundary driven inward, the shield shrinking around us. How far inward depends entirely on how dense the gas we enter turns out to be. A modest increase would pull the boundary in by tens of astronomical units and leave the planets untouched. A dense enough cloud, far denser than anything nearby, but not unheard of in the galaxy, could in principle drive the heliopause inside the orbits of the planets, so that the Earth itself would spend time outside the Sun's magnetic shelter, exposed directly to the interstellar medium and to the full flux of galactic cosmic rays. The atmosphere would still protect the surface from the worst of it. We would not be sterilized by simply drifting into a cloud, but the upper atmosphere would change. The rate of certain chemical reactions high above us would shift, and more interstellar dust and gas would reach the inner solar system than does now. None of this would happen quickly. The Sun would take many thousands of years to cross such a boundary, and the changes would unfold over a span longer than all of recorded history. No one alive would notice it beginning. It is not a threat in the way a falling rock is a threat. It is a slow change in the weather of the place we live, on a timescale so long that a civilization could rise and fall entirely within a single stage of it. And that second possibility is not a hypothesis with no precedent. It has happened before. The evidence is at the bottom of the sea, and as it turns out, in fresh snow. In 1999, a group of physicists in Munich published a result that should have been impossible. They had been studying crusts of ferromanganese from the floor of the Pacific Ocean rock that grows so slowly, a few millimeters in a million years, that a single centimeter is a deep core of geological time. Using an extraordinarily sensitive technique that can count individual atoms of one kind against a background of a billion others, they search these crusts for a particular form of iron, iron-60. Iron-60 is not made on Earth. It is forged in massive stars and scattered by supernovae, and it is radioactive, with a half-life of about 2.6 million years. That number is the key to the whole thing. Any iron-60 present when the Earth formed, 4.5 billion years ago, decayed away almost entirely within the first few tens of millions of years. There should be none left. So if you find iron-60 in ocean crust that is only a few million years old, it did not come from Earth and it did not come from the Sun's birth. It arrived recently, from space, from a star that exploded near enough for its debris to reach us. The Munich team found it, and they found it not smeared evenly through the core but concentrated in a distinct layer, corresponding to an age of about 2.5 million years. It was the signature of a specific event, a supernova close enough that its ejected material physically rained down onto the Earth and settled into the deep sea floor. Later work, led by researchers including Brian Fields and Anton Wallner, found a second, older pulse of iron-60, laid down between roughly 6.5 and 8.5 million years ago. Two separate signals, two separate nearby explosions, or two waves of the same series of them. The two layers tell a story when you place them against the sky. The massive stars that end as supernovae are not scattered randomly. They are born in clusters and move together through the galaxy in loose herds called moving groups, drifting along shared paths for tens of millions of years. Astronomers have traced back the motions of one such group of stars and found that it passed relatively close to the Sun in roughly the window when the iron was deposited close enough that, as its heaviest members exhausted their fuel one after another and detonated, their debris could reach the solar system. The two layers of iron in the seafloor, then, may not record two isolated accidents. And, quote, they may record two chapters of a single long passage, the Sun drifting near a cluster of doomed stars, and those stars dying, one and then another, over millions of years, each death dusting the Earth with a little more of its ash. We were not struck once. We spent a stretch of deep time living beside a group of stars that were going off like slow, scattered fireworks, and the sea floor caught the fallout of each. The younger and better defined of these signals has been dated with real precision, because ocean crust grows so slowly and so steadily that its depth is a clock. Reading down through the layers, the iron appears, peaks, and fades across a span corresponding to a few 100,000 years, around 2.5 million years ago, not an instant, but a prolonged reign, consistent with debris arriving and settling over a long period rather than falling all at once. And then the story became stranger and more immediate. Wallner and his colleagues went looking for Iron 60, not in ancient rock, but in fresh Antarctic snow. Snow that had fallen within the last few decades, and they found it there too. Iron 60 is falling on the Earth right now, in small amounts, drifting down onto the ice at the bottom of the world. The most natural explanation is that the Sun is currently passing through a region still laced with the debris of those ancient supernovae, that the local cloud itself may be, in part, the scattered remains of stars that died a few million years ago. We are not merely near the graveyard, we are moving through it, and it is still settling on us. More recently still, the same kind of analysis turned up atoms of plutonium-244 alongside the iron, a heavier, rarer signature, pointing to some of the most violent nucleosynthesis in the universe, the kind that may require colliding neutron stars, not merely exploding stars. That distinction points to one of the most extreme events the universe produces. A neutron star is already the compressed core of a dead star, a city-sized ball holding more than the mass of the Sunday. When two of them, locked in a shrinking orbit, finally spiral together and merge, the collision forges the heaviest elements in nature: gold, platinum, uranium, and rarer things still, and flings them outward in a burst of light and matter that astronomers call a kilonova. We have now watched one happen. In 2017, detectors on Earth felt the ripples in space itself, from two neutron stars merging in a distant galaxy, and telescopes swung to catch the glow. And in that glow was the signature of freshly made heavy elements. The plutonium sifting into the sea floor beside the interstellar iron may be a few atoms of just such a catastrophe, the debris of a collision between two dead stars, drifting through our patch of the galaxy, settling quietly onto a planet whose oceans it predates. The dust of catastrophes we can barely model is sifting down through the atmosphere as you lie here. The ocean floor and the Antarctic ice are not the only places the signal shows up. When the same painstaking analysis was applied to samples of lunar soil brought home by the Apollo astronauts, it found the interstellar iron there too settled onto the Moon, which has no ocean and no atmosphere to gather it, only bare rock exposed to open space. The Moon had been quietly collecting the debris of these explosions for the same few million years the Earth had, keeping its own record with no water or weather to disturb it. Two worlds, side by side, both dusted with the remains of the same dead stars. The technique that makes any of this possible deserves a moment, because the quantities are almost absurd. In a sample of ocean crust, the atoms of interstellar iron are outnumbered by ordinary atoms by something like 1,000,000 billion to 1. To find them, physicists use a particle accelerator to strip and sort the atoms one at a time, separating the rare heavy isotope from its overwhelming background by weight and by charge, and counting the individual survivors that make it through to the far end. They are, quite literally, picking specific single atoms out of the crushed rock of the seafloor and identifying each one by the kind of star that made it. That we can do this at all is why a supernova that exploded before there were oceans is not a matter of theory but a matter of measurement. There is a further consequence of the three waves that is easy to overlook. The compression of the shield and the destruction of the ozone do not simply happen side by side. they compound. A blast that squeezes the heliosphere inward at the very moment its cosmic rays are stripping the ozone means the surface is losing two defenses at once, each failure deepening the other, and not for days but for centuries or millennia. The biosphere would not face a single sharp blow and then recover. It would face a long, grinding erosion of its protection, sustained across more generations of most creatures than there have been human generations since we first stood upright. That is the true shape of the threat, not a flash and a healing, but a prolonged exposure that a living world either adapts to or does not survive. The supernova that laid down the younger layer has been traced, tentatively, to a loose group of hot young stars called the Scorpio-Centaurus Association, some 400 light-years away, containing stars of the right mass and age to have exploded at roughly the right time. Both of these associations belong to a larger structure, a great ring of star formation a few thousand light-years across, tilted against the plane of the Milky Way. It is a nursery and a graveyard at once. Stars are born there, burn hard and fast, and die young, and a supernova goes off somewhere within it, every few 100,000 years. Human beings have watched stars die, without ever knowing quite what they were seeing. In the year 1006, observers across China, Japan, the Arab world, and Europe recorded a new star in the southern sky, so bright it cast shadows and could be read by at night for weeks. The brightest stellar explosion in recorded history. A supernova a few thousand light-years away. Half a century later, in 1054, Chinese astronomers noted another new star, this one bright enough to be seen in daylight for more than 3 weeks. The shredded, still expanding wreckage of that explosion is the Crab Nebula, and at its heart spins the neutron star the blast left behind. In 1572, the astronomer Tycho Brahe watched a new star flare in the constellation Cassiopeia, and in 1604, Johannes Kepler recorded another, the last supernova seen with the naked eye inside our own galaxy. Every one of these was far enough away to be a wonder rather than a threat, but each was the death of a star, witnessed by people who had no framework for what a star's death was, written down as an omen, a portent, a light that came and slowly faded. None of the stars near us now is poised to explode soon enough, or close enough, to be a genuine danger, and that is worth saying plainly, because the point of all this is not that catastrophe is imminent. The nearest bright star that will end as a supernova is probably Betelgeuse, the red shoulder of Orion, roughly 600 light-years away. When it goes, which could be tomorrow night or 100,000 years from now, since we cannot read its inner clock, it will blaze in our sky as bright as a half moon and be visible in daylight for months, and then fade. At 600 light-years it is far too distant to harm us. There is no known star close enough and ready enough to threaten the Earth in any span of time we can foresee. The danger the iron in the seafloor records is real, but it is the danger of deep time, of the millions of years over which the sun drifts through the galaxy, and its luck, good and bad, slowly turns. The iron in the sea is proof that some of those deaths have been close, but the iron itself was never the danger. The iron is merely the receipt. There is a longer arc to this that is easy to lose behind the talk of danger. The same debris that a nearby supernova flings across the galaxy, the iron, the oxygen, the carbon, the heavier metals forged in the star's final moments, does not simply fall onto planets and vanish. It enriches the interstellar medium. It mixes into the great clouds of gas between the stars, seeding them with elements that were not there before, and when one of those enriched clouds eventually collapses under its own gravity, it forms new stars, and around them, new planets, built in part from the ashes of the old. Every atom heavier than hydrogen and helium in your body was made this way, cooked inside a star, scattered by its death, drifting through the galaxy for millions or billions of years, gathered into the cloud that became the sun, and finally assembled into a world, and an ocean, and eventually into you. The supernovae, whose iron sits in the sea floor, are not only a hazard, they are also, on a longer timescale, part of the same slow machinery that made the sea floor and the planet under it, and the eyes that will one day read the record. The galaxy builds and destroys with the same materials, in the same places, and does not distinguish between the two. The danger is everything else a nearby supernova delivers, and it arrives in waves. The mechanism has been modelled in detail by researchers including Adrian Mellott and Brian Fields. A supernova, within about 100 light-years close, in galactic terms would strike the solar system in a sequence, each blow arriving on a different timescale. The first wave is light. The initial flash, lasting minutes to hours, includes a pulse of gamma rays and X-rays that slams into the upper atmosphere and tears electrons from atoms. The immediate casualty is the ozone layer. High-energy radiation breaks apart nitrogen molecules, which then attack ozone and convert it into other compounds. Within weeks, a large fraction of the planet's ozone can be destroyed, and ozone is what absorbs the sun's ultraviolet light. Strip it away, and the ultraviolet reaches the surface at levels lethal to the small, exposed organisms at the base of the food chain, the plankton in the upper ocean, on which nearly everything else depends. The chemistry of that first wave is worth following, because it explains why the damage lasts. The radiation splits ordinary nitrogen molecules in the upper atmosphere, and the fragments recombine into nitrogen oxides, the same family of compounds that forms in the heat of a lightning bolt. These compounds are catalysts. A single nitrogen oxide molecule can destroy many ozone molecules in turn, surviving each reaction to attack the next. So a modest amount of them can eat away a large fraction of the ozone layer and go on doing so for years, drifting through the stratosphere until they are slowly rained out. The same compounds tint the sky, giving it a brownish cast and dimming the sunlight that reaches the ground, so the surface is struck at once by more ultraviolet from above and less visible light for photosynthesis. A double blow to the green things and the drifting plankton that feed everything else. Kill enough of the plankton at the base of the ocean's food web, and the loss climbs upward through every creature that depends on them, level by level, over years. The supernova does not need to touch a single animal directly. It only needs to poison the air for long enough that the bottom of the food chain gives way. The second wave arrives years to decades later and lasts far longer. Cosmic rays, accelerated by the expanding blast, reach the solar system. If the heliosphere has already been compressed by the supernova's pressure, these particles pour in more easily, deepening and prolonging the destruction of the ozone. Some reach the ground. When a cosmic ray strikes the upper atmosphere, it produces a shower of secondary particles, including muons-heavy, short-lived cousins of the electron that can travel all the way to sea level and even some distance underground. At high enough intensity, this rain of particles raises the rate of genetic damage in living things, generation after generation. Not a sudden kill, a slow pressure on the biosphere, a rise in the background rate of mutation and death, sustained over thousands of years. The third wave is the slowest, and in some ways, the most consequential. The physical shell of the supernova gas and dust, expanding at hundreds of kilometers per second, reaches the solar system thousands of years after the flash. This is the wave that compresses the heliosphere. Melot's models show that for a supernova within 50 to 100 light-years, the blast can drive the heliopause inward to roughly the orbit of the Earth. The termination shock would be pushed inside the inner planets. For a stretch of thousands of years, the Earth would sit largely outside the Sun's protection, exposed to the raw galactic cosmic ray flux with only its own atmosphere and magnetic field for defense. It is worth pausing on what that means in ordinary terms. Right now, at the surface where you are lying, the cosmic ray dose is low. The atmosphere shields you, and the heliosphere and the Earth's own magnetic field shield you further, cutting the flux of high-energy particles by a large factor. Strip away the heliosphere, and the surface dose would climb not to the instant lethality of standing beside a reactor, but to a chronic, elevated level, persistent across many human lifetimes, biologically active over the timescales on which species rise and fall. And the fossil record from around 2.5 million years ago, at the boundary between the Pliocene and Pleistocene epochs, does show a turnover in ocean life, the loss of certain large-shelled creatures, a shift in the communities of plankton. No one claims a supernova was the sole cause. The climate was changing too, the ice ages were beginning. But the radiation may have been a stress multiplier, a thumb on the scale, pushing already struggling species over the edge. The receipt for the explosion is in the rock. The bill may be written in the extinctions. The larger dangers do not stop with supernovae, and they do not require a star to be close. On the 27th of December 2004, a wave of gamma rays and X-rays swept through the solar system. It came from a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than the Earth's, So strong it would erase the information in a credit card from halfway to the moon. So strong it distorts the shape of atoms. A magnetar is what a certain kind of massive star can leave behind when it dies. In the collapse, the dead core is compressed to the density of an atomic nucleus, and whatever magnetic field the star had is compressed with it, wound and amplified until it reaches a strength found nowhere else in the known universe. There are perhaps only a few dozen of them catalogued in the whole galaxy, because the intense field decays over thousands of years and the object goes quiet. But while it is young and active, the field is under such enormous stress that the rigid crust of the neutron star can crack a starquake, releasing a spasm of energy in an instant. The largest of these releases, called giant flares, can briefly outshine the entire rest of the galaxy in high-energy radiation. That is what reached the solar system on a December day in 2004. This particular object sits on the far side of our own galaxy, roughly 50,000 light-years away, so distant that the flash we received had been travelling since before the last ice age. And yet, when it arrived, it was bright enough to physically affect the Earth. Satellites in orbit detected the spike instantly. Several were partially blinded by it, their detectors saturated, designed as they were to measure far fainter events at cosmological distances. The radiation ionized the upper atmosphere and briefly compressed the layer of charged particles that circles the planet, pressing it downward as if by an invisible hand, disrupting long-range radio signals for a few minutes. It caused no lasting harm, but the principle it demonstrated is sobering. A single star on the opposite side of the galaxy, 50,000 light-years away, reached across all that distance and touched the atmosphere of the Earth. Had it been 10,000 light-years away instead, the flash would have been strong enough to damage the ozone layer. Had it been within a few thousand light-years, the surface would have taken a dose comparable to a nuclear detonation overhead. Magnetar flares of this size are rare, only a handful have ever been recorded. But they happen, and they happen in our galaxy. Rarer and more violent still is the gamma-ray burst, the most energetic explosion known, produced when a very massive star collapses into a black hole, or when two neutron stars spiral together and merge. In either case, a narrow jet of gamma rays is fired along the axis of the collapse, concentrated into a tight beam, rather than spread in all directions. If that beam happens to point at the Earth, the effects are catastrophic, even from thousands of light-years away. A gamma-ray burst aimed at us from within the Milky Way would strip the ozone almost completely in seconds, and transform the chemistry of the atmosphere for years afterward, filling the sky with compounds that block sunlight and cool the planet while the ruined ozone lets ultraviolet through. The event itself would be over before anyone could register it. The aftermath would last a decade. What makes a gamma-ray burst so lethal at such distances is that it does not waste its energy. An ordinary supernova throws its light in all directions, so that its brightness falls away quickly with distance. A gamma-ray burst instead focuses much of its output into two narrow beams, fired in opposite directions along the axis of the collapsing star, like the beams of a lighthouse, concentrated that tightly. The radiation stays deadly across thousands of light-years, but only if you happen to lie within the narrow cone of the beam. This is the one mercy in the arithmetic. For any given burst, the chance that its beam points at us is small, because the beam is thin and the sky is wide. The danger is not that a burst will surely find us, but that, over hundreds of millions of years, with countless bursts firing across the galaxy, the odds of one eventually catching the Earth in its beam stop being negligible. It is a rare event multiplied by an enormous stretch of time, and deep time is exactly the timescale on which life on Earth has had to survive. There is a real suspect for such an event in the deep past. The extinction that ended the Ordovician period, about 445 million years ago, wiped out something like 85% of marine species, and its pattern is peculiar. It fell hardest on the creatures living in shallow, sunlit water, the ones most exposed to ultraviolet light, and spared many of those that lived deep or buried in sediment. That selectivity is what a gamma-ray burst would produce. The evidence is entirely circumstantial. A burst leaves no isotope in the rock, no iron-60, nothing to hold in your hand, because it produces only light. But the chemistry and the pattern of who died align with the model. Melott, who worked on the supernova connection, has also published on this possibility. His conclusion is careful and honest. A gamma-ray burst is a plausible trigger for that extinction. and we cannot rule it out. We also cannot prove it. It sits in the honest inventory of things that may have happened and cannot now be checked. There is one more class of dark object, quieter than any flare or burst, and far more numerous. When a massive star collapses to a black hole, the explosion is rarely perfectly symmetric, and the asymmetry gives the newborn black hole a kick sometimes hundreds of kilometers per second, enough to fling it out of its birthplace to wander the galaxy alone. There may be 100 million such isolated black holes drifting through the Milky Way, invisible, betraying themselves only when they happen to bend the light of a star behind them, or stumble into a cloud of gas and flicker briefly in X-rays. Most will never come near us. The galaxy is vast, and 100 million wanderers spread through it are still, on average, far apart. But over hundreds of millions of years, some pass closer. A rogue black hole crossing within a few light years of the Sun would not swallow us. The odds of a direct approach are minuscule. It would do something subtler. Its gravity would stir the Oort cloud, the immense spherical shell of icy bodies that surrounds the solar system, out to perhaps 100,000 astronomical units, and send a slow shower of comets falling inward over the following millions of years, raising the odds of an impact on Earth. Not a sudden catastrophe, a slow loading of the dice. The Oort cloud is worth pausing on because it is the part of the solar system almost no one pictures, and it is enormous. Long-period comets, the ones that fall in from the dark on orbits that take thousands or millions of years, come from a faint spherical shell of icy bodies surrounding the Sun, far beyond the planets, reaching perhaps a quarter of the way to the nearest star. It is loosely held. The Sun's grip out there is so weak that a passing star, or a drifting clump of gas, or a wandering black hole can nudge some of those distant ice balls onto new paths that carry them plunging into the inner solar system over the following millions of years. Most burn up or sail past. A few strike planets. Some geologists have looked for a rhythm in the record of large impacts on Earth, wondering whether comet showers triggered by the Sun's passage through denser regions of the galaxy might leave a faint periodic signature in the ages of the great craters. The evidence for any such rhythm is weak and much disputed, and it may not exist at all. But the mechanism is real. The outer solar system is a loosely held reservoir of frozen ammunition, and the galaxy occasionally reaches in and stirs it. None of these things, supernovae, magnetars, gamma-ray bursts, wandering black holes, can be predicted or prevented or in any way met. They are simply features of the galaxy we live in. The same galaxy whose exploding stars forged the iron in your blood and the oxygen in your lungs and the calcium in your bones. The processes that made it possible for you to exist are the same processes that could one day end you. The universe uses the same furnace for both, and it keeps no separate ledger. That is not a lesson. It is only the arrangement of things, sitting quietly behind everything we have learned tonight, the shield that protects us, thin and flexing, and occasionally broken, and the dark that presses on it from outside. Which brings the story back, at the end, to the two machines that told us all of this, and to the silence that is coming for them. The silence is coming not because the mission failed, but because it succeeded far beyond anything its builders imagined. Voyager 1 and Voyager 2 were designed for 4 years. They have run for more than 47, and the plutonium that powers them has been decaying the entire time, losing about 4 watts a year, without pause, indifferent to how much we would like it to stop. The available power on each spacecraft is now less than half what it was at launch, and the team that keeps them alive has spent the last several years making a sequence of quietly heartbreaking choices. The project is led now by Suzanne Dodd at the Jet Propulsion Laboratory, with a small team of engineers and scientists, some of whom have spent their whole careers with these two machines. They know each instrument by the character of its data, the quirks of its calibration, the voice of the scientist who built it, and one by one, they have had to turn those instruments off. Of the 10 instrument packages each spacecraft carried, 7 were switched off years ago, their planetary work long finished. Then, more recently, the harder cuts began, the cuts to the instruments that were still doing real science at the edge of the solar system. In the autumn of 2024, Voyager 2's plasma instrument, the one that had given us direct measurements of the interstellar medium, was shut down. In February of 2025, the cosmic ray detector on Voyager 1 went dark. In April, of 2026, engineers sent the command to switch off Voyager 1's low-energy charged particle instrument, a detector that had run almost without interruption since 1977, nearly 49 years, and that had helped map the pressure fronts and density changes in the space beyond the heliosphere. The command took some 23 hours to arrive, and the shutdown itself took a little over 3 hours to complete, out there in the dark, with no one to watch it happen. The decisions are forced by arithmetic that cannot be argued with. Every active instrument draws power. Every heater that keeps the fuel lines from freezing draws power. The radio that speaks to Earth draws power. Harmut draws power. To keep a spacecraft alive to the next milestone, something must be sacrificed, and the team weighs each sacrifice against the science it would end. In early 2025, during a routine turn, Voyager 1's power dropped unexpectedly close to the threshold that would trip an automatic protection system and begin shutting things down on its own, a process that would be dangerous to reverse from a day away. The team acted first, choosing which instrument to lose rather than letting the spacecraft choose for them. There is something quietly extraordinary about the people who make these choices. The engineers who built the Voyagers are, most of them, gone or long retired. The knowledge of how the spacecraft actually work, the quirks of a 50-year-old computer, the meaning of a particular pattern of errors, the way a command has to be phrased, so an aging memory will accept it, has had to be passed down, carefully, from one small group to the next, like an oral tradition kept alive around a fire. Some of the current team learned the craft from the original builders directly, in the years before those builders retired. They maintain paper documentation, decades old, for hardware that no one manufactures anymore. When a problem arises, they cannot simply look it up. They have to reconstruct, from the records and from the memories of people who are no longer there, how a machine designed in an era before the personal computer was meant to behave, and then reach across a day and a half of empty space to correct it. To keep the Voyagers alive is not only an act of engineering, it is an act of remembering. And still, the machines surprise their keepers. Years ago, the team turned off a heater that kept one of Voyager 2's instruments warm, expecting the instrument to fail in the cold. It did not. It kept working at temperatures far below anything it had ever been tested for, because the engineers who built it in the 1970s had, without being asked, given it a margin no one would need for decades. The Voyagers keep working past the edges of their own specifications, because the people who made them assumed they would one day be pushed past those edges and built accordingly. There is a lesson in that about how to build things that last, but the machines do not need us to state it. They simply keep running. There was one moment, recently, when it seemed the running might end. In late 2023, Voyager 1 began sending home data that made no sense, a stream of repeating, unreadable nonsense where its measurements should have been. The spacecraft was alive, its heart still beating, but it had stopped making sense, as though it were talking in its sleep. For months, the engineers worked the problem across a gap of nearly a full day each way. They traced it, finally, to a single failed chip in the memory of the flight data system, a piece of hardware storing part of the code the spacecraft needed to package its data. They could not replace the chip. Instead, they rewrote the affected code and tucked the pieces into other corners of the aging memory, sending the new arrangement across 24 billion kilometers and waiting nearly 2 days to learn whether it had worked. In the spring of 2024, Voyager 1 began speaking clearly again. It was, in a real sense, a repair performed on a patient farther away than any patient has ever been, by surgeons who could not see the patient and would not know for a day and a half whether the operation had succeeded. For the months the spacecraft was babbling, no one knew whether it would come back. It might have been the end, not a dramatic failure, no explosion, no last message, just a slow slide into permanent nonsense. The most distant human object reduced to a carrier tone with nothing behind it. When the first clean data returned, and the engineers saw the familiar patterns resolve out of the noise, there were people in that room who had worked on Voyager for their entire adult lives, and some of them wept. It is a strange thing to grieve for, or to celebrate a machine, an arrangement of aluminium and wire and decaying plutonium, coasting in the dark beyond the reach of any help. But it has been talking to us for longer than most people alive have been alive, and when it fell silent and then spoke again, the people who knew it best understood exactly what they had almost lost. The team is not finished fighting. As I speak, they are preparing a more aggressive power-saving plan, one they have nicknamed, with a certain dark humour, the Big Bang, that would switch off a group of power-hungry components all at once and replace them with leaner alternatives, buying more years of warmth and science. They are testing it first on Voyager 2, which has a little more power to spare and sits a little closer to home. If it works there, they will try it on Voyager 1, and if it works there, some of the instruments switched off in the last 2 years might even be woken again. Suzanne Dodd has said, more than once, that her goal is simply to see a spacecraft reach its 50th anniversary from launch a birthday that falls in 2027. They may make it, but the plutonium does not care about anniversaries, and sometime in the early 2030s, the power will fall below the level that can run even a single instrument, and then below the level that can keep the fuel from freezing and the antenna pointed at Earth. When that happens, even if some instrument is still generating data, we will never receive it. The great dishes will listen, and there will be nothing to hear. Those dishes are their own quiet marvel, and worth knowing before the signal stops. To speak with the Voyagers, engineers use the Deep Space Network 3 complexes of radio antennas, spaced roughly a third of the way around the planet from one another, at Goldstone in the California desert, near Madrid in Spain, and at Tidbinbilla in Australia, so that as the Earth turns, at least one of them is always facing out into the part of the sky where the spacecraft drift. The largest dishes are 70 meters across, their surfaces machined to a precision finer than a millimeter, their receivers chilled almost to absolute zero to quiet the whisper of their own thermal noise. When one of them turns to face Voyager 1 and gathers that tenth of an attowatt signal, it is collecting a beam that left the spacecraft nearly a day earlier and that has spread, by the time it reaches Earth, into a cone wider than the orbit of Jupiter. The dish catches a sliver of that cone, and from the sliver reconstructs a few tens of bits per second, and from those bits, the state of the space at the edge of the solar system. Every measurement we have from beyond the heliopause is an act of engineering patience stretched across the entire width of the solar system. There is a particular vulnerability in that arrangement, and it comes from the choice made at Saturn decades ago. When Voyager 2 was flung down past Neptune and Triton, its path bent it far below the plane of the planets, deep into the southern sky. And from the surface of a turning Earth, the far southern sky is only visible from the southern hemisphere. Of the 3 great antenna complexes, only the one in Australia can point far enough south to speak to Voyager 2, not merely to hear it, but to send it commands. There is exactly one dish on the planet that can tell that spacecraft what to do, and when it was taken offline for many months of upgrades a few years ago, Voyager 2 was left to coast in silence, listening for nothing, unable to be reached, until the dish came back. The most distant human traveller on that side of the sky depends, in the end, on a single machine in a valley near Canberra. Everything else about the mission is redundant and backed up and cross-checked. That one link is not, and when the Voyagers fall silent, there is nothing waiting to replace them. The orbiting mission that maps the boundary in neutral atoms, the Interstellar Boundary Explorer, will keep watching from near the Earth, but it watches from a distance and cannot touch the edge. The New Horizons spacecraft, which flew past Pluto in 2015, is coasting outward and may reach the termination shock in the 2030s or 40s, but it carries no plasma instrument and only limited detectors. It will glimpse the boundary, not measure it as the Voyagers did. Scientists have designed, on paper, exactly the mission that ought to follow a dedicated interstellar probe, built with modern instruments, aimed to reach the heliopause and press far beyond it, into the undisturbed interstellar medium the Voyagers are only now beginning to touch. Such a probe would be meant to travel faster than the Voyagers, to carry cameras and detectors those aged spacecraft never had, and to run for the better part of a century, outliving the people who launched it. It is a serious proposal, studied in detail, but it has not been funded, and it does not yet exist, and there is a hard truth in the arithmetic of such a journey. Even if it were approved and launched within a decade, it would take 20 or 30 years merely to reach the boundary, 244, and longer still to return the measurements that matter. The scientists who conceived it, in many cases, would not live to see its data. It is a mission that would have to be handed, like the Voyagers themselves, from one generation to the next, begun by people who accept that they are building something whose harvest belongs to their successors. And beyond New Horizons, there is nothing at all, no funded mission designed to reach the interstellar medium and report back. A dedicated interstellar probe has been studied and proposed and drawn up on paper, but it does not yet exist. And even if it were approved tomorrow, it would take decades to build and decades more to arrive. There will be a gap. A long gap, perhaps a full human generation, during which the only measurements we have from the edge of the solar system will be the ones already in hand, 2 continuous records, more than 40 years long, from 2 spacecraft on 2 different paths, through a boundary that never stops moving. When they end, we lose not just 2 machines, but the only window we have ever had, and the heliosphere will go on expanding and contracting and leaking and compressing without a single witness on the far side. There is one more thing each Voyager carries, and it was never meant to be read by us. Bolted to the side of each spacecraft is a gold-plated copper disc, a phonograph record, sealed in an aluminium cover, etched with instructions for how to play it. The astronomer Carl Sagan led the small team that assembled its contents in a matter of weeks in 1977, and the choices they made are strange and moving in equal measure. There are greetings spoken in 55 languages, from ancient Akkadian to modern Mandarin, some formal, some almost shy. There are the sounds of the earth itself: surf, wind, thunder, rain, a heartbeat, a mother's first words to her child, the calls of whales and birds, the noise of a human kiss. There are more than 100 images, encoded as sound, showing a fingerprint, a fetus, a snowflake, a person eating, the structure of the solar system. And there is roughly 90 minutes of music, chosen to represent the whole of the species, a movement of Bach, a Peruvian wedding song, a Navajo night chant, a raga from India, and, famously, a track by Chuck Berry, arguing, in effect, that this too is what human beings are. 2 details on the record hold more than the rest. Sagan worked on it with a writer named Anne Druyan, whom he would later marry, and Druyan asked to record the electrical activity of a human nervous system her own. In the days after they had privately admitted they loved each other, she lay in a laboratory while a machine recorded the impulses of her brain and the beating of her heart, thinking, as she did, of what it means to be alive and to be in love. Those impulses are on the record, compressed into a minute of sound, a human mind in a particular state carried outward forever, though no receiver may ever decode it. And on the cover, alongside the playing instructions, is a map, the same kind of map the pioneers carried, drawn by the astronomer Frank Drake, showing the position of the Sun relative to 14 pulsars, each marked with its own precise rhythm, so that a finder could locate our star in space and, from the slowing of those pulsars, in time. There is also a small sample of uranium on the cover, decaying at a known rate, a clock that will let a finder read how long the record has travelled. It was a message written by people who understood, better than most, how unlikely it was ever to be received, and who sent it anyway, not really to the stars, perhaps, but to themselves, a way of saying what they were while they still could. So consider, now, the image we began with, the dark room, the particles passing through your body trillions every second, mostly protons and light nuclei, moving at nearly the speed of light. They were accelerated by supernovae, by magnetars, by the magnetic turbulence of the galaxy itself, some of them tens of thousands of years ago. They crossed the heliopause, drifted through the magnetic froth of the heliosheath, past the termination shock and the outer planets, slipped through the thin upper air, and finally reached the roof, the ceiling, the dark above you, and then you. Most pass through without touching anything. A few strike an atom in a cell and leave a tiny track of damage which is repaired or is not. It is invisible, constant, and it does not know you are there. The atoms that make up your body were made the same way the danger was. The carbon in your bones, the oxygen in your breath, the iron in your blood were forged inside stars that died before the sun was born, and scattered by the same kind of explosions whose debris is still, tonight, settling onto the Antarctic ice. The shield that keeps the worst of the radiation off you is not permanent. It is a temporary arrangement of magnetic field and plasma, blown by a star with a finite life, and it has been squeezed to the orbit of the Earth at least once in the age of complex life, and will be again. The only thing that has changed is that we now know this. We are the first people who have ever known what the edge of the solar system is actually like, because 2 machines went there and told us before they died. They will not be there to tell us when the shield fails next. They will be drifting outward at 17 kilometers per second, cold and dark and silent, carrying their golden records, the whale songs and the thunderstorms, the greetings recorded in 55 languages, the 90 minutes of music from Bach to Chuck Berry into a galaxy that has no way to know what a record is. They will outlast the heliosphere that made them possible. They will outlast the sun itself. In 5 billion years, when the sun swells into a red giant and swallows the inner planets and the Earth with them, the 2 Voyagers will still be out there, somewhere in the dark between the stars, the last surviving evidence that this happened at all, that a species on a small world, having only just learned to leave it, built 2 machines and sent them past the edge of everything it knew, and found the space beyond stranger and more turbulent and more dangerous than it had ever imagined. The galaxy does not know we are here, but the knowing was ours. For a little while, we listened to a faint whistle from a machine at the edge of the sun's kingdom, and we understood, before the signal stopped, that the shield we live inside is thin and old, and not ours to keep. We learned what was pressing on the bubble, and we stayed awake long enough to say so.